The sun is the main source of natural light and illumination for the Earth. When the turning of the Earth brings on night, then we must turn to artificial sources of light for illumination. Here is our most familiar source of artificial light, the tungsten filament lamp. When an electric current excites atoms in the filament becomes luminous, giving off light because of the energy of its oscillating particles. Then the filament is said to be incandescent. The fact that a great amount of invisible infrared radiation is also being given off can be demonstrated by photographing this lamp with film sensitive to infrared rays. The image is brighter on the infrared film than on ordinary film sensitive to visible light, because less than 1/3 of the energy radiated is in the form of visible light. Tungsten filament lamps are not very efficient. The sodium vapor lamp, often used for street and highway lighting, is more efficient. Like other electric discharge lamps, it operates on the principle that visible light can be produced when an electric current is passed through a gas. In a sodium vapor lamp, because energy passes directly from electrons to atoms of the sodium, energy is converted more directly into light than in a tungsten filament lamp. Most of the energy radiated by the sodium vapor lamp is visible light. Neon signs operate on the same principle as sodium vapor lamps. When an electric current passes through the neon gas in the tubes, the gas glows, producing the characteristic red light. In mercury vapor lamps, mercury atoms are excited by an electric current. They produce an intense blue-white light, much of which is in the ultraviolet region of the electromagnetic spectrum. Fluorescent lights also depend on the conduction of electricity through mercury vapor. Inside this tube is a drop of mercury, which vaporizes when current passes through it, giving off ultraviolet light. The tubes are coated inside with materials called phosphors, which glow or fluoresce in ultraviolet light. This results in a softer light than the mercury vapor lamp produces. This panel produces a form of artificial illumination called electroluminescence. Phosphors on the panel are being made to glow by the changing electrostatic fields, which excite atoms in the phosphors. While there are many familiar forms of artificial illumination, when we measure the light they produce, we are usually concerned with only 3 quantities: the luminous intensity or brightness of the source, the luminous flux or flow of light from that source, and the amount of illumination on a surface. Let's begin with a measure of luminous intensity. Originally, the light from a burning candle of certain specifications was the standard for luminous intensity. It was the basis for the unit called the candle. Using this as a standard, all light sources could be measured in terms of their candle power. Today, candle power is more precisely defined in terms of the light emitted from incandescent platinum metal. The lamp that lights this glove compartment has a luminous intensity of about 1 candle. This 40-watt bulb has an intensity of about 35 candles. And this 40-watt fluorescent tube has an intensity of about 200 candles. While we are concerned with brightness of light when we measure luminous intensity, when we measure luminous flux, we're concerned with the flow of light from the source. Luminous flux is measured in this way. Let's consider this tiny lamp as a point source of light with an intensity of 1 candle. Now, we'll measure a distance of 1 foot from this point, and then construct a hollow sphere of 1 foot radius. We can assume light radiates equally in all directions from the point source. The flow of light through a distance of 1 foot to 1 square foot of the sphere's inner surface represents the unit of luminous flux, the lumen. 1 lumen of light flows to each square foot of the sphere's surface. Since the area of a sphere is 4 pi r squared, and r equals 1 in this case, the total number of lumens that are being radiated to the sphere must be equal to 4 times pi, or 12.57 lumens. This is the luminous flow from a source of light whose luminous intensity is 1 candle. So by knowing the candle power of a light source, we can determine the luminous flux by simple arithmetic. A lamp with an intensity of 35 candles will emit a luminous flux of approximately 440 lumens. And a 200 candle power lamp produces approximately 2,500 lumens. Also, because we know this relationship, a measure of the luminous flux gives us the candle power of a light source. This is a spherical photometer used to measure luminous flux. The lamp whose intensity is being determined is placed inside this white sphere. When the lamp is turned on inside the sphere, a photocell there measures the flow of light from the lamp. When we measure the amount of light that flows from a source to a surface, then we are measuring illumination. When there is a uniform flow of light perpendicular or normal to a surface, we express the illumination in this way. Illumination equals the number of lumens radiated to the surface divided by the area of the surface. If the area is in square feet, then illumination is measured in terms of lumens per square foot. This is a unit often called the foot candle. The foot candle is a unit of illumination equal to 1 lumen per square foot. Using this formula, we find that the illumination on a sphere with the light source at its center is this, since 4 pi r square is the area of the sphere. When the radius is 1, 4 pi times the radius squared is 4 pi times 1. But if we double the radius, changing it to 2, the radius squared equals 4. While all points on the 2-foot sphere are twice as far from the light source as they were on the 1-foot sphere, they get only 1/4 the illumination, because the luminous flux remains the same, while the area is increased by a factor of 4. As we increase the radius of this sphere, we will find that the illumination of points on its surface decreases as the square of their distance from the light source. Light energy is being spread out, which causes a decrease in illumination. So we can say this: illumination, if it is uniform, is directly proportional to I, the intensity of the light source. Illumination is inversely proportional to d squared, the square of the distance from the source. And this is called the inverse square law. We can explain this law in another way by thinking of light in terms of photons, the elemental units of light energy. As the photons move out from a light source, their number remains the same, but they are spread over a greater area. The number of photons per unit area is reduced, reducing the illumination. Understanding the inverse square law will help you understand how this device measures luminous intensity. This is called a jolly photometer. It is composed of a light source of known intensity, a light source of unknown intensity, and a slide made of 2 paraffin blocks separated by aluminum foil. The slide moves between the lights on a ruled board. Each block is illuminated by the light source it faces. The slide is moved until the 2 blocks appear equally illuminated to the viewer. Now we apply the inverse square law and set up a proportion. The intensity of this light is to the square of this distance, as the intensity of this light is to the square of this distance. The proportion looks like this. With 3 of the terms known, the 4th can easily be found. Thus far, we've considered only light which is perpendicular or normal to the surface it illuminates. As we tilt the card away from the normal, the illuminated area increases. Now, an area twice as large as the original one is being illuminated by the same light flow. Remember, we measure illumination in terms of lumens divided by area. So, with the same amount of lumens, but twice the area, there is half the illumination. That is, half as many lumens per unit area. With the card at this angle, we can say this. Illumination on this card is directly proportional to I, the intensity of the light, times 1/2. The illumination is inversely proportional to the square of the distance d from the source. If we were to measure the number of degrees the card has been tilted from its original position to double the area of illumination, we would find that the angle is 60 degrees. It would be easy to show by geometry that this is equal to the angle that the light makes with the normal to the surface of the card. If you've studied trigonometry, you know that the cosine of 60 degrees equals 1/2. So this relationship can be stated in terms of the cosine of 60 degrees. To apply this relationship to any angle, we can call the angle theta. Now we have a general formula which shows that the greater the angle that light makes with the normal to a surface, the less illumination there will be. That is, the less lumens per unit area. This same relationship helps explain the different climatic regions of the Earth and the changing seasons. Because of the inclination of the Earth's axis and the curvature of its surface, the sun's light strikes the surface at different angles at any given time. The greater this angle, the smaller the amount of light and heat that is received from the sun. So we have investigated sources of light, both natural and artificial. We have seen how luminous intensity relates to luminous flux and provides us with illumination.